Hey guys, my name is Mason. I'll be completely frank with y'all. Not the best at presentations, so don't go too off on me on the evaluations. I'm trying. But I did try to get ahead. The date that you see there, January 23rd, I believe that was last Monday, because I wanted to go ahead and knock this out, work on it, because this stuff's kind of interesting to me. I was a previous civil engineering background, even though we didn't talk much about these kinds of things like HVAC and stuff, but it's all kind of interesting to me, and I'm really excited to talk to you about it today. A lot of what I'm going to talk about is just the big picture concepts kind of thing. Talked with Dr. Kosak actually last Monday, and he wanted me to harp on specifically 4 special cases when it comes to heat gain and loss in buildings that the equations we're going to learn later won't really fit in with. Ethan and Megan did a great job on heat transfer mechanics, so a lot of what I'm going to be talking about as well is just some reiteration of those concepts like convection and radiation and all that stuff. Yeah, conduction. But let's go and jump right into it. So we should have already talked about R&U values. Dr. Kosak in this last lecture that he posted, did a really good job in explaining what this table was, and it's in your book, obviously page 200. In the PowerPoint there was a couple of images of some cross sections with different layers in it, and those are the different R values for like the the insulation, the resistance. And later we're going to be calculating what one specific cross section like layer, what the temperature would be depending on the temperatures on the outside and the inside and the other R values we have. And you already know up to this point that U, which is the heat conductance factor, is just the reciprocal of all the R values added up, 1 over R1 plus R2, etc. I can go on and on about this. Go ahead and get into internal temperature. I think Ethan talked about this briefly in his PowerPoint as well. I'm just going to reiterate it again. It's the temperature inside a wall roof. Pretty simple. It's important for considering vapor barrier location as well. I forgot word for word what the book talked about, but it's important to determine what our internal temperature is going to be depending on what the purpose of the building or the room itself is going to be for. And there's a lot of other factors that we have to determine in order to find the ideal internal temperature that's going to make everyone comfortable. That's how many people are going to be in there. That's what light fixtures you're going to have, what other appliances you're going to have. All those give off heat, and what infiltration we're going to have and ventilation too. So the other thing is that heat distribution is not going to be uniform due to the variation of the R values in given walls. And this is a good radiation example too. Heat transfer mechanism, surface temperatures on the walls and inside a room, especially windows, have a great impact on internal temperature. Especially windows. They can absorb a lot of heat and definitely heat up a room. And your book talked about this. I forgot which page it was on, but it was in chapter 15. The mean radiant temperature is just cold surfaces drawing radiating body heat, because we all know up to this point the main idea, heat flows downhill from hotter temperatures. Catch my breath. Went to the store and bought a really good cup of coffee, so I'm tired, but I am wired. All right, moving on. Infiltration. This is another factor of how we want our internal temperature to be. It's it can be natural. It actually is natural. I remember Dr. Kosak talked about it in his PowerPoint. This is just something that naturally happens. Air leaking into a building via poor construction quality, wind pressure, temperature differences. But if you have if you're remodeling or redoing a room inside a house or inside whatever building you have, like for example painting, you can open up all the windows and let that air dry out quicker. And what that section also talked about was air changes too, how much you're replacing the outdoor air per hour, but it's got to be converted to cubic feet per meter. Ventilation too, this is intentional. The lecture this week talked about that ventilation. We want to ventilate the exhaust air inside a building and replace it with fresh air from outside. It's brought in by certain apertures, brought in by certain devices we have. This table right here, I thought was pretty interesting as well, because it plays back into one of the other things I talked about earlier. Actually, not too earlier. Was one of the factors that determines internal temperature, and that could be how many bodies are in a room at a given point. So there you have it right there. Chapter 15 if you want to go back and look at it. Now we're talking about economic efficiency of outdoor air. There's really three main ways that the book talked about, and that's minimizing. So you're minimizing outdoor air means minimizing less heating and cooling costs. And I believe this was, I don't have my book currently in front of me because I have the PowerPoint taking up all my screen, but depending on hours of operation, a building can determine how much energy it uses to ventilate the building. So if they're closed on the weekends, they're not going to have as much energy to ventilate the building because there's not that many people inside of it, and vice versa. Heat exchangers transfers heat between exhaust air and incoming outdoor air. Can be used for odor control, which is good, without paying full price. Economizers are great. Describes air intake and dampers that permit the use of outdoor air instead of refrigeration. It's for building cooling when outdoor temperatures are just right. And the enthalpy economizer, which I thought was pretty cool, it actually calculates both outdoor and indoor conditions and determines what the best, economic efficient energy to use. So that's pretty interesting. And again, this is talking about heat gain and loss in buildings too. So ventilation, infiltration, and direction of heat flow are going to be some of the main ideas we're talking about here. And I'm going to get to the 4 special cases here in a second. So heat loss. All parts of the building's skin lose heat to colder surroundings. I mean, this is obvious. If it's cold outside, heat inside the building wants to flow outside. And the rate is determined by the U value of the conductance of the exterior. And how do we find the U value? We have to find the R values, which is what Dr. Kosak talked this week about. It's 1 over R1 plus R2 plus R3, etc. If you add up all the R values, you get the R total, and then you just convert it using the reciprocal. So that's how we do it. I would put these equations in here, but I somehow forgot to do that. If you want to go back and rewind it, you're more than happy to. You're more than welcome to. So outdoor area losses. Again, we're talking about heat and gain. Heat gain and loss. That's my bad. Well-sealed buildings have equipment that continuously replace indoor air with outdoor air to maintain quality. Heating equipment must be sized with the capacity to heat the air delivered to the building. Here we go. 4 special cases that do not work. So, like I said, these formulas that we're going to use to determine heat gain and loss in buildings, there's 4 special cases where they would not work. And the equations are given in the book, but I'm just going to be giving you the basic idea of it. So, ducts outside of the conditioned space. In this section of the book, there's a lot of good drawings that will bring to fruition what is being said here. Basically, if the duct's not in the insulation zone, it's going to lose a tremendous amount of heat, and engineers, designers, HVAC specialists, they're going to have to find a way to account for that heat loss when they're calculating the total heat gain and loss in a building. So, yeah, like I said here, they can add a percentage to the sum or just simply place the ducts inside the insulated zone. Basement walls and floors. You're talking about utilizing your geographical location for your gain. So the earth is a great natural heat storage. It has great natural insulation. Anything in contact with it is going to reap the benefits of heat insulation from that too. So when we're talking about straight heat gain and loss in buildings, you're going to have to use a different equation for that. And I believe is Q equals U times A, which is the square area times the temperature difference. I believe so. Unheated spaces, again, that's like I said here, spare rooms, closed attics, crawl spaces, anything that's really not open to the outdoor conditions, but really isn't supplied with some sort of heat ventilation, that could act as a little like an R value. there's an R value in that table I showed you before. It's like you have an air gap in airspace, and it has an R value tied to it. So, and then a slap edge too. Book didn't really go into this. It just gave you the formula, Q equals U times A times the temperature difference. And it can be used to calculate heat loss through the exposed edge of concrete floor construction. And there's a figure in your book, figure 15.7. It says it allows 1 square foot of area for each linear foot of slab. I am not the best artist, but there is one that will do it better justice in your book. So that will be figure 15.7. You want to go back to that. So when we're talking about heat gain and loss in buildings, the main idea is that you need to know the direction of heat flow and the other factors that go into how are we going to keep the internal temperature comfortable, and what materials do we have, and what do we need to calculate. That's the bottom line. So I'm excited to learn new material for this week. Again, I did my best in trying to prepare this presentation, and I read a lot up on it as best I could. So thank you again, guys, and see you later.